So this is our last chapter for the semester. We're looking at chapter 9, which is going to be dealing with lipids. So just to give you an idea of what lipids are, they're a family of biomolecules that have the common property of being soluble in an organic solvent. So that means that they're nonpolar, so they dissolve into nonpolar solvents. And there are many different kinds of lipids that will serve a variety of functions. Most lipids have hydrocarbons or modified hydrocarbons, and many are esters or amides with long hydrocarbon chains, which are called fatty acids. So we're going to look at just kind of overview what we're going to be talking about. So we are going to look at fatty acids first of all, and then waxes, triacylglycerols, glycerophospholipids, sphingolipids, steroids, and then the last one we aren't really going to cover, so we're probably just going to stop at steroids, and then we're going to talk about the cell structure, the membrane structure. So last one we're really not going to cover. Okay, so just looking at the structures first, and then we'll get more in depth into each of these. But waxes are esters with a long hydrocarbon chain for both the carboxylic acid portion and the alcohol portion. So here is the ester right there. And then over here is the alcohol portion. Over here is the carboxylic acid portion. They mostly have protective functions. Again, we're going to talk about that more later. But for now, just know that a wax contains an ester bond with the carboxylic acid, hydrocarbon chain being pretty long. I mean, for that one, there's 15. And then on the other side, the alcohol portion, there's 30 carbons there. So we'll get more into looking at what waxes are and what they do, but for now, just know that it does have an ester bond. Next, we're going to talk about triacylglycerols. They're also called triglycerides. So triacylglycerols have three triesters that are with glycerol. So glycerol just looks like this. It has CH2 with an OH, and then CH with an OH, and then CH2 with an OH. So there's 3 hydroxy groups on glycerol, and at those spots, at each of these hydroxy groups, we can form the ester bond right there. So there's 3 ester bonds. Okay. So for triacylglycerols, they're a major form of energy storage for animals. And again, we're going to talk more about that function later. But just so you know right now, triacylglycerols contain those 3 esters. We're also going to look at glycerophospholipids. These are triesters of glycerol also, but instead this one has a phosphate group that's attached to the glycerol. So we have 2 fatty acids attached to the glycerol, and then a phosphoric acid attached to the glycerol. So it looks a little bit different. Just give you a general idea here. So it will have the glycerol right here like this, and then we have 2 fatty acids and then the phosphoric acid right here. So each of these points right here are going to be an ester bond connecting the glycerol. So I guess I could label that glycerol. Again, we'll look at the structure again, but for now, glycerophospholipids look like this, with the glycerol, the 3 triester bonds attaching the fatty acids and the phosphoric acid all together. So they control the flow of molecules in and out of the cells. And then sphingomyelins are amides. So far we've seen esters, and now sphingomyelin actually has an amide bond that is formed from an amino alcohol that's called sphingosine. So we'll look at that structure later. It contains an ester bond as well to a phosphoric acid. And these are important to cell structure and nerve cell membranes. Then last for this group is glycolipids. They're similar. They have amide bonds as well that are derived from sphingosine. But instead of a phosphoric acid, they contain a carbohydrate group. And these are on the cell surfaces, and the carbohydrates interact with intercellular messengers. Okay, so again, we'll get more into that later on. Okay, then we're going to cover sterols. Like I said, we're not really going to get into icosanoids. Sorry, can't talk. But both of these don't have either an ester or an amide. Okay, so these are a little bit different. They're still lipids. They're just not, they're a little bit different because they don't have those esters or amides. So sterols contain a 4-ring steroid nucleus structure. So sterols are always easy to spot because they have these 4 rings right here. Okay, so they're pretty easy to spot those and know it's a sterol. Icosanoids are carboxylic acids, and they deal with intercellular chemical messengers, but again, we're not really going to focus on that, just so you can see the structure there. So the carboxylic acid portion is right here. Okay, so first of all, we're going to look at fatty acids. Fatty acids are carboxylic acids with long hydrocarbon chains, and most naturally occurring fatty acids have an even number of carbon atoms usually between 12 and 20 carbons. And then the hydrocarbon chain with all single bonds is referred to as saturated. And then if the hydrocarbon chain has a double bond, then it's referred to as unsaturated. So we talked about saturated and unsaturated in chapter 2, and we said that alkanes were considered saturated because they had all single bonds, and then alkenes were unsaturated because they contained double bonds. So in this, if we do have a saturated fatty acids, they take on the same properties as alkanes, whereas unsaturated fatty acids take on the properties of alkenes. So here's some examples. The first is palmitic acid, and it contains all single bonds. So it's considered saturated, and you can see, I mean, it's pretty straight. I mean, there's a zigzag, because of the tetrahedral geometry, but I mean, across the board here, it's pretty straight. So here is the carboxylic acid portion of the fatty acid right here, and then it's just all carbon and hydrogen after that. Okay, our unsaturated fatty acid is linolenic acid, and it has 3 double bonds. So we've got a double bond here, here, and here. Okay, and the double bond can be cis or trans, just like we saw in alkenes. And all of these look to be cis, right? So let me go back here. So we can see the hydrogens are on the same side there, and then here, and then here. So all the hydrogens are on the same side, making each of those bonds cis. So instead of having that nice straight line like the saturated fatty acid did, this one kind of curves around like this, so it's not so straight. Okay, and again, here's our carboxylic acid portion of the fatty acid. So saturated and unsaturated fatty acids are a bit different. The structure looks a little bit different because of those double bonds. So fatty acids are represented with a shorthand notation. So for palmitic acid, it says C16 and then O. So the C16 means that the chain has 16 carbons in it, and 0 means that it has 0 double bonds. And then there's stearic acid there, same thing, it has C18, so there's 18 carbons in the chain and 0 double bonds. So these are the most common of our saturated fatty acids. And then we have oleic acid, which has C18-1, so 18 carbon in the carbon chain, and then 1 double bond is located in that hydrocarbon chain. And then linoleic acid has 18 carbon in the chain, and then this one has 2 double bonds located in the hydrocarbon chain. So these are the most common unsaturated fatty acids that we have. Then last of all, linoleic and linolenic, these are hard to say together, are essential in the human diet because the body does not synthesize them. So these are omega-6 and omega-3 fatty acids. So we have to take these, we have to make sure that they're in our diet because again, they are essential to the human diet and we can't produce them, so we have to ingest them. Okay, next that we're going to look at are waxes. Okay, a wax is a mixture of a fatty acid and a alcohol, and they're combined in the ester bond. Okay, so the red represents the carboxylic acid portion, and then the blue is the alcohol chain portion, and then the ester bond is right here. Okay. So very similar to what we learned in our carboxylic acid chapter. So for the waxes, each carbon chain can be from 16 to 36 carbon long. So you can see on this one, we have 15 carbon chain, and over here we have 30. So they can get very long on both sides. Waxes are found mainly in plants and animals, or not mainly. Waxes are found in many plants and animals, and then natural waxes can be found on the surface of fruits, leaves and stems of plants, and they're also found on skin, fur, and feathers. So earlier I told you they have provide protection properties. So this is external protection for all of these things. So for skin and fur and feathers, it protects it from water, or for the plants it protects it from bugs and other things. Anyway, so protective properties for waxes. Oops. Okay, next we're going to look at triacylglycerols. So in the body, fatty acids are stored as triacylglycerols. They're a major form of energy storage for animals. This is basically animal fats and oils. Those are the two things we're going to be looking at. They're the most plentiful lipids in nature. So even though some are in solid form while others are liquid, they still have the same structure. Okay? All fats and oils contain 3 ester bonds between glycerol and 3 fatty acids. So here's our example here. So here's glycerol right here. So they form 3 ester bonds right here, here, and here. Okay. To form the triacylglycerol. So that's what it looks like. The glycerol reacts with the fatty acids to form those ester bonds. So here's an example of a trisylglycerol. We have the glycerol right here. Okay. And then we have the ester bonds right here, 3 of them. And then if you look, we have 3 fatty acids, but they're all different. So anytime this happens, you know, you're not necessarily going to get the exact same fatty acid in the trisylglycerol. So here we have palmitic acid, which is a saturated fatty acid. So again, that just means that it has all single bonds. Then we have an unsaturated fatty acid, which is oleic acid, and it has double bonds. So it has 1 double bond right there. And then linoleic acid, also unsaturated, has 2 double bonds in it. So oils contain fatty acids that have large amounts of fatty acids with 2 or more double bonds. Okay, so oils are going to have those unsaturated fatty acids in them. And then fats contain fatty acids that are mostly saturated. So because of that difference, because oils do have the unsaturated fatty acids, or a higher proportion of unsaturated fatty acids, they're going to cause them to have a lower melting point than animal fats will, okay? Because remember, animal fats have these saturated fatty acids in them. So just to give you an idea of why they are different and why they have are at different states, here is stearic acid. So we're just looking at a single fatty acid here, but this is stearic acid, and it is saturated. So again, when we were looking earlier, that saturated fatty acid is pretty straight, okay? There's no bends or turns or anything in them. It's pretty straight across. And then here is an unsaturated fatty acid. Again, this is just a single unsaturated fatty acid. And you can see that double bond causes this curve to happen. So it says 2 cis double bonds, okay, causing it to curve like that. So, you know, if you have mostly unsaturated fatty acids coming together to form that trisylglycerol, and you've got all these curves, you know, that's what's causing it to be in that liquid state, whereas those saturated fatty acids, when they come together, are going to be mostly straight and have pretty strong forces holding them together. Okay, trisylglycerols are neutral and nonpolar, and they are hydrophobic molecules. So these molecules will come together when stored in fatty tissue. That's what, you know, they coalesce, so they come together. And then again, their primary function is energy storage, and the adipose tissue will provide insulation and padding, protective padding. Trisylglycerols can undergo reactions, so they're going to be very similar to reactions we have seen already. So the first one is hydrogenation. So we saw this in chapter 2 when we were looking at alkenes. But hydrogen can be added to the carbons that are in the double bond. And remember, when it does that, it just removes the double bond. So this is the exact same reaction we looked at when we were doing alkenes. So here are the 2 double bonds. We have hydrogenation take place. And now, instead of the double bonds, we have hydrogens. So we went from a unsaturated fatty acid to now a saturated fatty acid. So when you do a complete hydrogenation in an oil, you know, you've taken away all the double bonds and you've added the hydrogens. When you do that, it gives a brittle product. But if you only partially hydrogenate the oil, it will change from a liquid oil to a soft semi-solid fat. So this is how margarine and shortening are made. Okay, just partially hydrogenating those double bonds, and causing it to become a fat, right? It's no longer an oil, now it's a fat. But if you only partially do it, it will be a soft fat. You know, it won't be the same. So we can have that. We also have hydrolysis. Okay, so this is very similar to the hydrolysis we talked about when we were looking at esters. Okay, because triacylglycerols have 3 ester bonds there, and so when they are hydrolyzed, they give the glycerol, right? So here's the fat or the oil, and when it's hydrolyzed, now we have glycerol by itself, which would be the alcohol portion, right, from when we were doing hydrolyzing esters. And then we have if we do it with, if we do the hydrolysis with water and a acid catalyst, then we'll just produce 3 fatty acids right there. Okay, but here in this example, we are doing hydrolysis using a base. Okay, so NOH is the base and water. And when that happens, it's just like the reactions from the ester hydrolysis that we looked at. Okay, we're getting the carboxylate salts. Okay, we get 3 of them here. So it's a carboxylate salt because we've got the O and the Na. Okay, so it's making them 3 carboxylate salts here. Okay, and this is this example of the saponification. So we're producing soap in this reaction. So be sure to remember those 2. Again, you can have hydrolysis of triglycerols with water and a strong catalyst, a strong acid catalyst, and then you can do it also with water and a base, and then you produce the soap. Okay, last of all, I just wanted to mention how, for this video, I want to mention kind of how soap works. So the sodium salt end, so just going back here, sodium salt end, what I'm talking about is this end right here. Okay, we have a negative and a positive. Okay, that is hydrophilic, which means it's water loving. Okay, and then the other portion, the R group over here, okay, is hydrophobic, because you have just that hydrocarbon chain, right? Long hydrocarbon chain. So that's going to be hydrophobic. So you've got 2 ends, hydrophilic and hydrophobic. So right here, we've got our hydrophilic end, which likes water. Over here, we've got our hydrophobic end, which doesn't like water, okay, because it's nonpolar. So when the soap is put into the water, the molecules are able to come together and form what's called a micelle. So we've got right here inside, we've got these the nonpolar hydrocarbon chains. So remember, they're hydrophobic, and so the hydrophilic ends out here all come together, okay, because they like water, and it kind of makes this little ball to protect the hydrophobic end. So it's very similar to when we talked about proteins and how they form a pocket. The hydrophobic interactions form that pocket, you know, in the protein. So this is happening, but instead with these triacylglycerols, the hydrophilic ends are coming together and the hydrophobic ends are in the middle. So what happens as they're coming together, losing my spot here. So the hydrophobic tails are in the middle, and well, before the micelles form, grease and dirt will interact with the hydrophobic tails, and then that micelles formed, and the dirt and the grease gets trapped in the middle of the micelle. So then you can just easily wash away the soap, and it takes with it the dirt and the grease because it's trapped inside, you know, right in here. Okay. So that's kind of how detergent works, and again, it gets trapped in that hydrophobic area, so it makes it a lot easier to get rid of it and just rinse it off.